In this video, we're going to look at solving for the stopping distance, looking at cars as our main example. So let's say you're driving down the street and you see something ahead of you. We're going to call that thing the stimulus, in this case, a walrus. You're driving ahead with some initial velocity, and we'll call that VI. When you see this walrus, you're still traveling, and it takes your brain about 1.5 seconds to actually clue in to what you're seeing, and then to send a signal to your foot to slam on the brakes. And so during this time, this is called our reaction time, we're moving at constant velocity. And so the displacement during this time, and we're going to call this D1, D1, that's going to equal our initial velocity multiplied by the time. And this time here, this is our reaction time. Now, if once our brain says, oh no, we need to stop, we're going to slam on the brakes, and then we're going to still travel forward while we decelerate. And while we're decelerating, we have to use two formulas to determine our distance. So the first formula we're going to use is to figure out the time. Now, our final velocity is 0 meters per second. Car comes to a complete stop. And so we're going to use this formula, acceleration equals VF minus VI over time. We know that our final velocity is 0, and so we can rearrange this for the time is going to equal negative VI over A. Now, because we're braking, our acceleration is going to be negative. It's going to be in the opposite direction of the way we're traveling. So this is the time required to stop after applying the brakes. It's not equal to the reaction time. Now that we know this time, we can use one of our two formulas we discovered during displacement. So we can either use displacement equals the average velocity, so final plus initial over 2 times the time, or we can use displacement is equal to our initial velocity times the time plus 1/2 AT squared. In both cases, we should get the same answer. So we're going to look at an example of this. All right, so what is the minimum distance for a car to stop upon seeing a yellow light at an intersection if the car is initially traveling at 60 kilometers per hour? So our initial velocity of the car is 60 kilometers per hour. We see that the driver's reaction time is 1.5 seconds. So the car is going to move for 1.5 seconds before the driver actually applies the brakes. And so this we're going to call displacement 1 or distance 1. And this is going to equal our initial velocity times that time. Once the brakes are applied, it's going to then take the driver some more time to stop. And so we know in this area, or in this second section here, we're going to call this D2. That's going to equal the average velocity during stopping, so final plus initial over 2 times the time. And then we have to solve for this time using our formula VI, negative VI over A. And so we're going to be able to figure out both of these distances, and we'll do that on the next slide. So we'll start with our first distance. So this is going to be distance during constant velocity. And we're going to call that D1. Okay, so we know we were traveling at 60 kilometers an hour. And we're going to change that into meters per second. So we're going to multiply by 1,000 meters over 1 kilometer, and then divide by 3,600 seconds in 1 hour. And we get 16.7, so 16.6 repeating meters per second. We know that our time is equal to 1.5 seconds, typical reaction time. So our kind of constant velocity distance is going to be 16.7 meters per second times 1.5 seconds. And we get 25 meters. So that's how far the car actually travels before the brakes are applied at all. Next, we're going to look at, we're going to call this D2, and this is the distance during braking. So we know that our final velocity is going to be 0 meters per second because we come to a stop, and our initial velocity is 16.7 meters per second. And we were told that the car is going to decelerate at -6 meters per second squared. We're going to use these values to determine the time that it takes to stop. So acceleration equals VF minus VI over t. And so we can rearrange that formula. That time is going to equal VF minus VI over A. VF is 0, but we can keep it in the formula just to be safe. So 0 minus 16.7 meters per second divided by -6 meters per second squared. Now you should end up with a positive number because time can't be negative. So if you end up with a negative number, just check your math again, make sure you didn't drop a negative sign anywhere. And it takes 2.78 seconds for the car to come to a stop. So this is the braking time. So now we have this time, we can use our displacement formula. So the average velocity, so VF plus VI times the time. We know VF is 0 meters per second, we can include it anyway, plus 16.7 meters per second over 2, multiplied by our braking time, which is 2.78 seconds. So I'm not rounding when I do this math until the very end. So I'm keeping all of these numbers in my calculator. And here we get 23 meters. So that's not our total distance. So this is our distance during braking. The total distance that the car travels is going to equal D1 plus D2. So this is the reaction time distance. And D2, this is our braking distance. That's going to equal 25 meters plus 23 meters. And so in total, it's going to take us 48 meters to come to a stop once we see that yellow light.